We are in section 2.6 talking about rational functions. We're going to talk about rational functions this entire time. It's a big topic, and we'll spend a lot of time in class working problems. Okay, so first of all, this is the definition of a rational function. It has a numerator and a denominator, and both of the numerator and the denominator are polynomials. So here's an example of a specific rational function. Okay, so let's start with domain. When we have a rational function, there's a denominator, and so you have to worry about dividing by 0. So your domain in rational functions is all reals except for any time the denominator equals 0. So here's my example function. I'm going to take the denominator and set it equal to 0 and solve for x. I get x equals 1. Therefore, my domain is all reals other than the number 1. Okay, so that's your domain. Well, what happens in graphs of rational functions is wherever you have a value where you don't have the domain. So, for example, in this case, at x equals 1, one of two things occurs. You either have a vertical asymptote or you have a hole, one of those two things. And so in this lesson, we're going to focus on figuring out whether or not there are vertical asymptotes or holes at the places where we do not have any graph, where the domain does not exist, where the graph does not exist. Okay, so when is it a hole? The hole is whenever the denominator equals 0 and the numerator equals 0. So you'll get a 0 in the numerator and the denominator. Vertical asymptotes, however, the numerator does not equal 0. But the denominator does equal 0. So here's an example. I think this is our leading example. Still, x cubed minus 3x squared plus 2x. So in this example, if I set the denominator equal to 0, so I'm going to set the denominator equal to 0. X minus 1 equals 0. X equals 1. I'm also going to set the numerator equal to 0. That would be x cubed minus 3x squared plus 2x equals 0. Okay, to solve this, you have to factor. Every term has an x in it, so I can factor out an x. Then I can factor this binomial here. This will be x minus 2, x minus 1. I get 3 zeros. At x equals 0, x equals 2, and x equals 1. Notice x equals 1 is a location, an x value, in which both the numerator and the denominator equals 0. Therefore, we have a hole at x equals 1. Well, holes are coordinate points, right? Holes are coordinate points. They're exactly non-points, but they have an x value and a y value. And you need to figure out what the y value is whenever you have a hole as well. So in order to do that, you're going to take your original rational function, go ahead and factor and cross off, because that's why you have a hole, is that x minus 1 will actually cancel. So I'm going to do that over here. So I'm looking at that function and factored. See, I already factored it. The numerator is x, x minus 2, x minus 1. And the denominator doesn't need to factor. It's x minus 1. And x minus 1 cancels. And so everywhere except for at 1, f of x would be equal to x times x minus 2. If I plug 1 into that, I get 1 times 1 minus 2. I get negative 1. This tells me the y value of the hole, the y value of the location of the hole. So this is at 1, negative 1. You will have holes and different rational expressions, and you will have to plot them. Okay. The next important topic in rational functions is to talk about the other kinds of asymptotes, horizontal asymptotes and slant asymptotes. The way that I teach horizontal asymptotes and slant asymptotes is really simple. I just have you do long division. You have to know long division no matter what, so you know it anyway. You do long division. Whatever you get as your answer is your asymptote without the remainder. You can just ignore the remainder. So if you get some sort of constant like 4, then y equals 4 is your horizontal asymptote. If you get a line, then that's your slant asymptote. So I have 3 examples here. We're going to do all 3 examples, and you'll see the different kinds of horizontal or slant asymptotes that you can get. So you take your denominator, and you take that into your numerator. Well, in this first example, so I'll call this number 1, the denominator is bigger than the numerator, right? The degree on the bottom is 2, the degree on the top is 1. That goes 0 times. It goes 0 times, and then I would have a remainder, but it goes 0 times. This has a horizontal asymptote at y equals 0. Horizontal asymptote of y equals 0, because it went 0 times. All right, and the next one, I fixed in question 2 here, I fixed the degree of the numerator. Now it's big enough. So when I perform the long division, x squared plus 1 goes into 2x squared. How many times? Well, only look, whenever you're doing this, remember, only look at the first term here and say, what can I multiply this x squared by to get a 2x squared? And that would be the number 2. So when you multiply everybody. So 2 times x squared is 2x squared plus 2 times 1, that's 2. You would subtract this, and we would have a remainder of negative 2. This remainder, negative 2, is smaller degree than my denominator, so I can't go any more. And so this has a horizontal asymptote, again, because I only got a constant y equals 2. So this has the horizontal asymptote y equals 2. The last one here, I've changed my 2x squared to an even higher degree of 2x cubed. That's going to make me have a slant asymptote. So let's see how the division works out now. So when I take x squared plus 1 into 2x cubed minus 2, now I need to multiply x squared by 2x in order to get 2x to the third whenever I multiply through. And then I would have plus 2x, right? 2x, because if I multiply by the x squared, I get 2x to the third. Then times the 1, I get 2x. Now you're supposed to subtract this. And the way this subtracts, this 2x to the thirds cancel. These two right here are not alike, so they can't combine. I have negative 2x minus 2 left. I think a lot of times you guys would leave blanks or holes there, zeros, so that you wouldn't be tempted to add not like terms. But now this doesn't go anymore, does it? X squared does not go into 2x. So this is my remainder. And again, you just totally ignore the remainder. It doesn't matter. And so now I have y equals 2x. This is no longer a horizontal asymptote because I got an x. That's a line that's slanted. This is a slant asymptote. Y equals 2x. And that's all there is to horizontal and slant asymptotes. You just simply do long division. Okay. So ultimately, the questions that we're going to do, we're going to be graphing rational functions. And there are so many different features in the graphs of rational functions. We have gone over just a few right now, but I ultimately want to know all of these features in rational functions. It's going to take us like 10 minutes to do one problem. I know, it's very exciting. So I have steps for how to graph every rational function, and this, if you follow these steps, you will it will ensure that you talk about every sort of interesting feature I'm concerned with. So the first things we do are we set the numerator and the denominator equal to 0. Let's see here. I have these mixed up. So if you were writing this, turn them around. So the first thing to do is set the denominator equal to 0. That tells you the domain. Okay. It also tells you if that there are holes and or vertical asymptotes. So what you do next is you set your numerator equal to 0. That's how you figure out your holes or your vertical asymptotes. When the numerator equals 0 and it's not a hole, then that's your x-intercepts. Because we care about x-intercepts. That's a question we've been answering a lot. The next question is, what are the y-intercepts? So steps 1 through 3 we've already done. So y-intercepts, you make x0. Then we also just did number 4. You're going to do long division to find any horizontal asymptotes or slant asymptotes. Okay? Now, number 5 is a little different. It says, I want you to do a sign chart. And I will do that when we do this next example. But when you do the sign chart, the points that you plot on the sign chart, your points of interest, are x-intercepts and vertical asymptotes, where anytime the denominator and the numerator are equal to 0, and or the numerator, you just throw them all in there, unless they're both equal to 0, because that's a whole and it doesn't matter. Next, check for symmetry. And we've done that already. And then you're going to sketch. Start with your asymptotes, then plot your holes and intercepts with your sign chart, connect them, and hug all the asymptotes. Okay, so what does all of this mean? So once you've got this written down, take it with you. We're going to do this example. All right, my function is 2x cubed minus 2 over x squared minus 1. Before I even do anything, I'm going to go ahead and factor this. Okay, so x cubed minus 1 factors, and you should know how that factors. A difference of cubes factors this way. I'll give you the formula in a second. Okay, so this is f of x factored. Dealing with the factored form is way easier, way easier. Okay, so let's set step 1, let's set denominator equal to 0. So that means x plus 1, x minus 1 equals 0. So I get negative 1 and 1. So my domain is all reals. X cannot equal plus or minus 1. Okay, one of those is a hole, one of them is a vertical asymptote. We're going to see that when we set the numerator equal to 0. When I set the numerator equal to 0, dealing with my nice pretty factored form, that's 2x minus 1, x squared plus x plus 1 equals 0. So 2 doesn't equal 0. X minus 1 equals 0 when x equals 1. And x squared plus x plus 1 will not equal 0. If you do the quadratic formula, you'll actually get imaginary numbers. 1 minus 4. So you'll get an I, so no real answer. You'll get complex imaginary answers, but no real answer. Completely real. Okay, so I actually have no x-intercepts here because x equals 1 isn't an x-intercept, it's a hole. All right. So let me find, so I have a vertical asymptote at x equals negative 1. That is from, the vertical asymptote is from this one. Here the denominator equals 0, but notice the numerator did not. But I also have a hole, and the hole is where x equals 1, because that is x equals 1 and then is a 0 in the numerator and the denominator. Let me go back here to the factored form, and let me cancel the x minus 1. Now, if I plug 1 into what I have left, so this is what I would have left after I cancel the x minus 1. If I plug 1 into that, I get 2 times 1 plus 1 plus 1 over 1 plus 1. So this is 3. So my hole is at 1, 3. Okay, so let me see. The next step is to find y-intercepts. The y-intercept is just simply make x 0, and that's actually easiest to do in this form. So if x is 0, y is 2. Okay, now let's work on horizontal asymptotes. You also want to work in your non-factored form for horizontal asymptotes. So I'm going to take x squared minus 1. So this is step, I think that's step 3 or 4. X squared minus 1 into 2x cubed minus 2. All right, so I need to multiply x squared by 2x. That would get me 2x cubed. And now I multiply 2x by minus 1, and I get minus 2x. When I subtract this, be careful to just subtract. That's 2x minus 2, and that's too small. So this is my remainder. And I have y equals 2x as a slant asymptote. All right, I'm going to try to summarize my findings over here. So I have a slant asymptote at y equals 2x. All right, looking back at my directions, so that was actually all the way up to step 4. Step 5 is to do a sign chart. So let's talk about this sign chart here. So my sign charts are very simple. They're not these big complicated tables. And we're going to do sign charts later on in the year too. So pay attention. This is definitely something we're going to do more than once, especially when we get to the calculus portions. So on this sign chart, I'm going to put important numbers. And the important numbers you put are your x-intercepts, which I have no x-intercepts. Maybe I should write that down. X-intercepts, none. Then also you want vertical asymptotes. So I had a vertical asymptote at x equals -1. That's going to go on there. And that's it. Vertical asymptotes and x-intercepts. Okay, then the next thing we're going to do is you're going to look at your original function all the way up here. 2x cubed minus 2 over x squared minus 1. Let me write it here. And actually, the factored form might be a little bit easier, but I only have 2 places to test. So what I do is I pick a test point in each division of the real line. I only had one division here. That's the only one at -1. So I pick a number between -infinity and -1, like -2. I'm going to take -2 and I'm going to plug it into my expression, and I decide whether or not I get a positive or a negative. In the numerator, I would get a positive, and in the denominator, I would also get a positive. Because in the numerator, I'd get a negative. -2 squared is -8. So I have negative something minus something else. So that's like negative something over 3, because -2 squared is 4. 4 minus 1, positive. So I have a negative over a positive, and a negative divided by a positive is negative. The next number I'm going to test is a number between -1 and infinity, like 0. So I'm going to test 0 here. When I plug 0 in, I get negative over negative. That's positive. All right, knowing these signs is going to help me when I figure out my final graph. All right, step 6, check for symmetry, and then finally sketch the graph. All right, so let me check for symmetry. I'll do that down here. A lot of these will have no symmetry, but we'll check anyway. So I plug -x in. 2 times -x cubed minus 2 over -x squared plus 1. This is -2x cubed minus 2 over x squared minus 1. Notice that it's not completely opposite and it's not completely the same because of that negative. So there's no symmetry. No symmetry. All right, so let's graph it. Here's my graphing. We're going to put in the asymptotes first. I have a vertical asymptote at -1. I have a slant asymptote at y equals 2x. You have to be able to graph this line. So y equals 2x has a y-intercept of 0 and a slope of 2. So up 2 over 1. Up 2 over 1. Now, this is a dotted line. It's a vertical, or it's a slant asymptote. All right, let's plot my hole. My hole is at 1, 3. 1, 2, 3. So it's right here, just north of that asymptote. I have a y-intercept of 0, 2. That's this point here. And I think those are the only actual points I have, because I have no other intercepts, no x-intercepts. And I know that I have no symmetry. Now, right here, this sign chart, this negative tells me that my graph is negative when x is less than -1, and then positive after that. That tells me that my graph has to be here. All right, and I know that might have just thrown you, that might feel like it's in left field. But you have to hug asymptotes. Whenever you have rational functions, those asymptotes are like, they're like magnets, and the graph is just naturally attracted to them. The graph is naturally attracted to them. And so I cannot stay in this left portion over here of the graph and stay below the y-axis if I graph it here. That's not okay, because I cross into positive land, and I know from my sign chart that I stay negative. So I'm not going to have, I must be in this little quadrant there. And then if I use my points and I connect my points, I know that the rest of my graph is here. All right. There's one more example here, and I would like for you to try to go through all of the steps on this, okay? Do this at home, go through all of the steps that you can and try to graph it. Then when you come into class tomorrow, I'm going to check it and we're going to go through it in detail to see what you can get and what you can't get, individually, one by one.